In this problem, we are given the following circuit diagram. We need to find the Thévenin impedance seen looking into the terminals A and B of our circuit. We know that the frequency of our operation is also 25 kilorads per second. And since it's given in rads instead of hertz, we're going to say that our omega is equal to 25, since it's in kilo, times 10 to the cubed. So this is our omega. Now, to actually do this circuit, we need to have some kind of charge in here, because currently there's no initial voltage. So what we're going to do is add one right here, a test voltage. It's going to be plus minus like this, connecting our A and B, and it's just going to be a test voltage of 1 volt. This could be any voltage, but 1 volt is the easiest, so that's why we're using 1 volt. Now, to solve this, we know that our VT of H is equal to our TAB, and we know that this is in ohms. And we know that to get ohms, we can use Ohm's law, and we say that voltage over current. And we know that our test voltage is 1 volt. So now that we have our test voltage in here, all we need to do is find our current, and we know the current flowing here is our I delta. So we need to find our I delta. To do this, we're going to use the mesh current method, and we know that we're going to have some current going through this way, and this way. This is the direction of our current. We know that our voltage is going down like this, because the current would be flowing up like this. So in doing this, we know that all voltage in an enclosed space like this is equal to 0. So we will have a 0 is equal to, and then we will have a negative 1 volt. The reason why it's negative is because our voltage is going down and our current is going up. Now we're going to have our I delta, and this is being multiplied by all the impedance in our current area. So current is flowing through this capacitor. We need to use this capacitor, we need to use this resistor, and we need to use this resistor as well. What we need to do is convert it into our XC. And looking in the formula linked below the like button, in V-I relationship for a capacitor, we know that our X of C is equal to a negative J divided by omega times C. This is going to be negative 1 divided by, and then in here we are going to have our omega, which we know to be 25 times 10 cubed, and then we're multiplying this by our capacitance. So this is being multiplied by 10 divided by 3, and then this is being multiplied by 10 to the negative 9th, because we have a nano in here. And this is going to give us approximately negative 1200. So for our capacitance, we are going to have a negative J 1200. When we add all these impedance together, we're going to have a negative J with our 1200, and then we have a 1 kilo ohm plus 125 ohms. And we know that 1 kilo ohm is equivalent to 1000 ohms. So we're just going to have plus 1125. And these are both in ohms. This is both resistance. Our capacitance is ohms. Any impedance is ohms. Now we can see that our 125, if we're actually doing the mesh current method, is right next to the current flowing through this part of our diagram, because we're breaking it up. Now we can see though that this current is going to be represented here, and this current is actually flowing into our node, and it's flowing down like this. It's flowing down the same direction as our current from the first part is. So instead of subtracting this like we would normally do if it was going in the opposite direction, we are going to add them together. That means we're going to have a plus 19 I delta, and our I delta is going to be multiplied by our 125 ohm resistor, just as our I delta was here. So this is times 125, and this is going to be ohms, and we can combine these two. If we do 125 times 19, this is going to give us 2375 I delta. Now we can combine like terms. We're going to move the 1 volt to the left, and this is equal to our I delta. We have our 2375 plus our other constant, which is 1125, and this is going to give us 3500. So in here we'll have 3500 minus J 1200. And now we can find our I delta by having a 1 volt, and underneath this we're going to have 3500 minus J 1200, and that's equal to our I delta. Now we can plug this in as we know here. We are going to say that we have a 1 volt, because this is our voltage, over our equation that we have right here. Putting this over here, we can see that our volts are going to cancel out. This is just going to leave us with a 3500 minus J 1200 200. I did just realize that I made a pretty big mistake where when I wrote this down, I only wrote it as 1,200, and I've even stated that a couple times, but this should actually be 12,000. So we're going to have an extra 0 at the end here. And we can see from the calculation that we did earlier that I got 12,000, I just never wrote it. So that means this should be 12,000. We are going to also have a 12,000 right here. We are also going to have a 12,000 here, a 12,000 here, and then a 12,000 here. But that doesn't really affect the answer. That's the only thing that changes. So this is going to be the actual correct answer. And when we write it in our question, we're going to have 3,500 plus our J, which is already filled out, negative 12,000 ohms. And that's how you would write it. If you want more introduction to circuit analysis, there is a playlist as well as notes covering the entire coursework linked in the description below.